So, good morning, everyone. My name is Shashwat Yadav from CSE department here at Indore. Today, I will be representing semantics of big data. In this presentation, we will explore how semantic helps us understand the meaning, context, and interpretation of large and complex data. Let's begin with the basics of big data. Introduction to big data. Big data refers to extremely large and complex data sets that traditional data tools cannot handle efficiently. In today's world, data is being generated every second from social media, sensors, and many other sources. To describe big data, we use 5 V's: volume, velocity, variety, veracity, and value. Volume means the massive scale of data. Velocity is the speed at which it produced and processed. Variety refers to the many different data formats like text, images, videos. Veracity means how reliable the data is, and value shows how meaningful insights can be extracted from it. Big data is extremely important in modern computing as it powers AI and smart decision making in fields like healthcare, finance, and marketing. What is semantics? Now let's talk about semantics. Semantics is the study of meaning interpretation. In simple words, it's about understanding what data actually means. In computing, semantics helps system understand relationships and context between data elements, not just the raw values. For example, one system might use the term customer ID while another uses user ID. Both refers to the same person, but unless the system understands the meaning, it can't connect the two. That's where semantic comes in. It gives data shared meaning and prevents confusion when integrating information from multiple sources. Need for semantic in big data. Big data comes from multiple diverse sources, all with different formats and naming conventions. Without semantics, integrating or combining this data becomes very hard. For example, two datasets might refer to the same customer using different column names. Semantics helps the system understand they are the same and align them properly. It also improves interoperability, meaning different applications and departments can easily share and use data. Another key is context-aware analysis. Semantics allows systems to analyze not just the data itself, but the meaning behind it, making insight much smarter and more relevant. Semantic technologies. Semantic technologies are tools that give structure and meaning to data. Some of the most important ones are ontologies, RDF, OWL, and Sparkle. An ontology defines the concepts and relationships within a particular domain. It's like knowledge map. RDF stores data as subject predictive object triples, forming a graph structure that links data points. OWL Web Ontology Language builds on RDF, allows more complex logical relationships between them. And Sparkle is a query language used to extract and manipulate data from RDF module. Together, these technologies help computers not just to store data but truly understand it. The semantic layer. The semantic layer is a critical part of big data architecture. Think of it as bridge that connect raw data to meaningful insights. This layer translates unstructured data into a common format that can be easily understood across systems. It ensures that all data entities like customer products have consistent definitions and relationships. With semantic layer, organization can perform context-aware analytics which leads to better decision making and intelligent data recovery. Semantic integration. Semantic integration is about combining data from multiple systems based on meaning rather than the structure. Instead of matching column, it links information by understanding what each piece of data represents. For example, in smart farming, semantic integration can connect weather data like rainfall or temperature with crop yield data. This allows farmers to find useful pattern and correlation that wouldn't be visible if those datasets were separate. It also supports entity linking and data confusion, helping system maintain context and relationships while merging data from different sources. Semantic integration also enables context-based search, where users can search based on ideas or relationships, not just keywords. Role of ontologies. Ontologies play a central role in semantics. They define how different entities, concepts, and relationships are connected within a specific field. For instance, in healthcare, an ontology can connect patients, disease, treatments, and outcomes in one structured framework. This helps create a shared understanding across medical systems. Ontology also ensure consistent terminology across teams and organizations, which is essential for accurate data interpretation. In short, ontologies give meaning to data and help bridge communication between humans and machines. Let's look at the key benefits of using semantic in big data. First, it improves data quality and consistency by enforcing shared definitions. Second, it enhances search and discovery, allowing users to find information based on meaning, not just a keyword. Third, it increases interoperability, enabling smooth data exchange between different systems. Fourth, semantics supports contextual analytics, whereas insights are more meaningful and relevant. And finally, it simplifies integration of diverse data sources, even unstructured ones like text or images. Overall, semantics transforms data into a well-connected knowledge system. Challenges in semantic data. Despite its benefits, applying semantic in big data is not easy. One challenge is building and maintaining large ontologies. It takes time and expert knowledge. Another is computational complexity. Reasoning over huge datasets can slow down performance. Data privacy is also a concern because linked data may reveal sensitive information. And finally, there is the issue of standardization. Different industries use different semantic models, making integration difficult. So while semantic offers powerful solutions, it also requires careful designs and resources to implement effectively. Real world applications. Semantic is already making a big impact in the real world. In smart cities, it connects IoT data, traffic systems, and public services to manage resource flexibly. In healthcare, it integrates patient data, clinical trials, and research to support better treatment and diagnostic. Knowledge graphs like Google Knowledge Graph use semantic to improve search accuracy and recommendation. In e-commerce, semantic personalization connects customer intent with related products. And in social media, semantic sentiment analysis helps companies understand public opinions more deeply. This example shows how semantic turns massive data into meaningful and actionable performance. Knowledge. Conclusion. To conclude, semantic adds much needed context. and meaning to big data. Without semantic, data is just raw and disconnected. By applying semantic technologies, we can transform isolated data silos into intelligent knowledge systems. This not only improves analytics but also enables smarter, more human-like understanding of information. The future lies in combining AI and the semantic web. AI can automate ontology creation, and semantics can make AI more explainable and accurate. Together, they lead us towards intelligent ecosystems where machines truly understand the meaning of data, not just the data itself. Thank you for listening.